Hi, and welcome to 7.4H, Banked Turns and Conical Pendulums. The H stands for honors, and those things sound kind of honorsy. It's kind of weird. In this lesson, students will be able to calculate the centripetal force of objects traveling in uniform circular motion in scenarios where it is necessary to break vectors into components. So vector components coming back into the fold. Critical thinking. Highways in areas with cold winters are subject to hazardous conditions such as icy roads. How would you design turns on a highway to decrease the chance of cars slipping as they make the turn? Pause the video and think about how you could make turns on highways and roads safer. Did you say make them into crazy ramps like this? Now, this is a picture from, I think it was like Mercedes test ramp or something like that. Um, you got to bank that turn a little bit. Now, this is an extreme example, but you got to bank that turn. So as a car travels around a turn, the frictional force acts as the centripetal force. Banked turns are used to help the frictional force move the car in a circular path. So besides friction, what type of force is acting as the centripetal force in this type of banked turn? Now, again, this is a racetrack, but you could see a very slight curve. Have you ever noticed that on a highway before? There's a slight incline on these curves. And it's there for a reason, not just because they messed up and it's sliding to the right. No, they put it there. Why? Why did they put it there? What force is helping the frictional force make the turn? What force is helping to act as the centripetal force? Pause the video, think about it. Did you say the normal force? Or maybe it's just a component of the normal force. This car is making a circular turn here. Which component of the normal force is pointing in the direction of the center of the circle? Remember, centripetal force, center-seeking force. The x component of the normal force is helping the car turn in the circle. It is the part of the center-seeking force. So this normal force, because it is a banked turn, this part of the normal force will help the frictional force make the turn. So we had done a do now. It says consider the car in the do now. What angle should the road be with the horizontal in order to navigate the turn safely without the use of friction? Let's say it's a super icy road. Uh, so no friction is helping, only that component of the normal force. Okay, what would this angle have to be so that that component of the normal force that we just talked about is enough to make the car move in a circle? Remember from the do now, in case you didn't do it, it says the car's mass is 1,500 kilograms and it's approaching a turn with a radius of 100 meters at 30 meters per second. So let's do it. No friction, all right, because friction will make it a little bit trickier. So no friction. What does the angle have to be in order for the car to successfully make the turn? So the first thing we want to do is make a free body diagram. All right, gravity's pulling straight down, and we have that normal force that is perpendicular to the surface. All right, 90 degrees to the surface. It's like an inclined plane problem. And this time we're going to break the components into X and Y. Last time we encountered inclined planes, we did the parallel and the perpendicular direction because most of the things were acting in that direction. But now, why would it be helpful to have X and Y? Well, in the Y direction, this Y component of the normal force is balancing out the weight, okay? And in the X direction, why is it important to have this X direction? As we said earlier, this X component of the normal force is acting as the centripetal force. So this is equal to FC. And that's why it's useful to go back to the good old X and Y axes when we do our analysis. So in the Y direction, it is in equilibrium. You're not jumping off the turn and you're not going through the road. So we could say that the net force in the Y direction is equal to the normal force, which is positive, pointing up, minus Fg. All right, so we set up the definition of the net force is it's the sum of all the forces. The next step is to say, well, what's happening for the net force? Is the object accelerating? We just said it's in equilibrium, these forces balancing each other out, so we know the net force is equal to 0. We also know the y component of the normal force is adjacent to the angle, so we can do the shortcut method, the hypotenuse, Fn, times the cosine of theta, so that's that, and then Fg is equal to mg. So we have a handy formula for Fn. Fn cosine theta is equal to mg. All right, so let's take that and let's look at the x direction. In the x direction, there's only one force, and that normal force, because there's no friction, remember, that x component of the normal force is causing centripetal acceleration. It is unbalanced. There's no other force in the x direction, so it's definitely unbalanced. It's not in equilibrium, so the net force is going to be equal to ma. All right, but we're moving in a circle now, so it's equal to mac, the centripetal acceleration. So that's a little preview of like the concept that we're doing. This is equal to mac. Let's write it out formally. So the net force in the x direction is equal to the x component of the normal force. All right, so the net force is equal to mac, there it is. And the x component of the normal force is opposite the angle. So we're going to use sine. This is the hypotenuse times the sine of the angle. It's the shortcut method for the x component. All right. Now these are opposite, I'm realizing now, of what the shortcuts normally are. Right. In the y direction, normally it's the y and the sine. That's actually in your reference table, but it's not always like that. You have to look at where the angle is. The angle is adjacent to y, so we use cosine, and the angle is opposite the x, so we use sine. So if that was a little confusing, just you have to look at where the angle is. All right, how did we jump here? Well, the centripetal acceleration is equal to v squared over r, so that's nice. And now I flipped it around here so that we could do the next step. So Fn sine theta is equal to mv squared over r. Now we have two equations. We could take these equations and we're going to divide them. Fancy trick. You could do this. You could take two equations and just divide them. All right. So if we divide Fn divided by Fn, that cancels out. And an m divided by an m, that's going to cancel out. And what are we left with? Sine theta divided by cosine theta is equal to v squared over r over g. Now, this is obviously an improper fraction. We want to address that. And do you remember what sine divided by cosine is equal to? That's the definition of tangent. So sine divided by cosine becomes tangent. And let's see, what did we do? We multiplied the top and the bottom by r. These canceled out. You're left with v squared over gur, or rig. All right, so rg. So now we have a handy equation that will tell us the angle, because you take the inverse tangent of both sides. That gets the theta by itself. Remember, you're just isolating the variable. And we have an equation for the angle. It has to do with the speed of the car, the radius of the turn, and what planet you're on. And that'll determine what angle you could go at. Remember, this is no friction helping you out, only the normal force providing the centripetal force. So in our example, we had a car with a mass of 1,500 kilograms, and that didn't matter because the masses cancel out. All right, but we have, let's see, V is 30 meters per second. All right, and then R is 100 meters, and we are on Earth. So the angle would be 42.6 degrees. Now try to picture that in your head. That is a huge banked turn. You wouldn't make this on the highway because they assume that there's going to be friction and it's not some hypothetical problem where there's zero friction all of a sudden and physics is broken. But just so you know, if you did have a curve that was like this, it could be super icy and you would still be able to navigate that turn of 100 meters at this speed and you'd be fine. But if you go faster than this speed, you'd fly off the hill this way. And since there's no friction, if you go slower than this speed, you'd actually slide down the hill this way. So luckily there is friction. But that was a fun exercise, wasn't it? Banked turns. Okay, so how does this experiment relate to banked turns? We've seen this diagram in previous lessons, and in class, this is a classic lab to do, and not around your finger like this. There's an apparatus. They call it the centripetal force apparatus. You don't want to wrap the string around your finger like that. But this is, a classic thing that you could do in the classroom, and there's some experiments that you could do with that. But how does it relate to banked turns? And if you weren't spinning it super, super fast, if you're just gently spinning it, would it really be, this is a hint, would it really be completely horizontal, this circle? Hmm. Okay, I'm going to give you the answer now. This relates to banked turns because it's actually like this. There's an angle over here. All right, and now hopefully you can see it's gonna start looking like the inclined plane banked turn problem that we did. Let me ask you something. What is the force that's acting as the centripetal force in this experiment? It is the tension. But if we were going to draw a line from the stopper to the center of this circular path, it would be pointing in this direction here, okay? Not in the direction of the string. Only a part of the string, the x component of the tension, only a part of the tension, the x component of the tension is acting as the centripetal force. So this is causing you to move in a circle. And what is this doing? Is it accelerating upward? This looks unbalanced to me. No, it's being balanced out by the weight of the stopper. So that's the full picture of what's going on in that classic lab experiment. Let's do some more with it. So this is actually called a conical pendulum. A conical pendulum consists of a weight or a bob fixed on the end of a string or rod suspended from a pivot. This would be the pivot, okay? Its construction is similar to an ordinary pendulum. Pendulums just swing back and forth, okay, back and forth in one direction. But this is a conical pendulum. All right, so it says, however, instead of swinging back and forth, the bob of a conical pendulum moves at a constant speed in a circle with a string or rod tracing out a cone. Hopefully you can see this is making a conical shape, a cone shape. All right, so that's why it's called a conical pendulum. All right, so this is an example that we could do. It says, in an experiment, a 1 kilogram rubber stopper is attached to one end of a 0.75 meter long string. A student whirls the stopper overhead in a circular path, forming a conical pendulum. The stopper completes 20 revolutions in 10 seconds. It is determined that the string is making a 60-degree angle with the vertical as shown in the diagram. Determine the tension in the string and find the tangential velocity of the stopper. So you might have noticed I rearranged this a little bit, okay? I made a triangle for the whole thing, and I put the y component of the tension, I just moved it over here, so this is head to tail, okay? And this angle is equal to this angle over here. Now what else can we say? We know the length of the string is 0.75 meters. Is that the radius of the circle that this is making? Let's take a look at the diagram. Is that the radius? Hopefully you're saying, no, that's not the radius. This is the radius right here. Okay, so whatever this distance is, that's going to be the radius. All right, so I'll let you think about how you would find that radius as we start the rest of this problem. So just like before, we have the net force in the y direction, and that's equal to the tension in the y direction minus Fg. So what else do we know? In the y direction, the net force is 0 because you're not moving up or down at all. You're not accelerating up or down. You also know that Ty is equal to the tension times, and then look at the angle over here. All right, this is 60 degrees right here. This is Ty. Is Ty opposite, adjacent, or hypotenuse to that angle? Ty is adjacent to the 60 degrees. So since we have adjacent and the hypotenuse, we're going to use cosine. And yes, that's different from the shortcut, again, that's in your reference table. But in this case, because they give you this angle here, all right, you could say T is cosine theta. If you wanted to, you could obviously find this angle and do it differently, but we'll just stick with what they gave us. They gave us this 60-degree angle, so we'll stick with that. And then obviously Fg is equal to mg. So continuing on, we're just solving for T, adding mg to both sides, dividing by cosine, and we could actually solve at this point. You have a tension in the string of 19.6 newtons. In the x direction, you only have the x component of the tension. And the x component of the tension is the center-seeking force that's acting as the centripetal force. That's the thing that's causing the thing to move in a circle. So the net force, what is the net force equal to? Yes, it's equal to the tension. What else can you say about it? It's equal to ma. It's accelerating in a circular path. There's centripetal acceleration. AC is equal to v squared over r. And the net force is equal to ma, Newton's second law. So this is Newton's second law in a circle. The net force is equal to mv squared over r. In the x direction, the tension is opposite the angle. So we have opposite and hypotenuse. So this turns into T sine theta. This is the shortcut, modified shortcut. So solving for V, okay, we're looking for the tangential velocity of the stopper. So all I did was multiply both sides by R, and then I divided both sides by M, and then I took the square root. So I'm solving, I'm getting an equation for V. Okay, so what else do we know? We know that the tension is equal to mg cosine theta. So I just plugged in this equation over here. That's the only difference there. What else do we know? We know the masses are going to cancel out, so that's nice. And we're left with r times g over cosine theta times sine theta. And you could rearrange this as rg sine theta over cosine theta. And then this is that nice definition of tangent. So V is equal to the square root of rg tan theta. Man, this is some fun stuff. It's going to get funner, more fun. All right. R, we said, ooh, it's not equal to 0.75. The length of the string is 0.75, but the radius of the circular path is definitely less than 0.75 because 0.75 is the hypotenuse of this bigger triangle over here. And we want to know what this leg of that triangle is. So if you know this is the angle, this is the hypotenuse, and you're looking for this, what identity would you use, right? R is opposite the angle, so you would use the hypotenuse times the sine of 60. So instead of R, you can write in L sine theta, and it's down here too. All right, so that's the shortcut. Modified shortcut, right? Because this is in the X direction and we're using sine, so it's a little weird on top of all the other weird stuff, but hopefully you're following me, right? So R just became L sine theta, and then we have the rest of it, G tan theta over here. Now, they don't like, look how messy this is. It'd be nice to have those trig identities all to one side. So let's just move it over like that. And now we can plug in our numbers. We know the length of the string, we know we're on Earth, and we know the angle. And we could determine that the velocity is 3.32 meters per second. Great job, except units minus 1 because you didn't write the units for 1 kilogram and 9.8 meters per second squared. 1 kilo, then this was 0.75 meters, and this is 9.8 meters per second. And if you left it like that, still units minus 1 because it's meters per second squared. So if you do forget your units when you're checking over your work, if you want to squeeze it in like this, that's fine. Do what you got to do. If you forget, except you catch yourself before you submit your test or quiz, you could squeeze in the units a little bit neater than what I did, but that's totally fine. Fun stuff. That's about it. Thanks for watching and have a great day.